Thank you very much, Mr. Felix. I want to welcome everyone to today's class. It's another wonderful time to share the knowledge we have together. However, I can see that there are very few people in class today. Hoping they will join us in the course of the class. Earlier this morning, I posted on the chat group a short exercise, just so we also get familiar with what we did yesterday, and from that exercise I could see that I've been getting response anyway, and everybody got almost everybody got the same answer, and I believe with that we can proceed. I want to believe we all have a good understanding of what was done yesterday. Or should I just start? Like, if you have any questions from yesterday's work, kindly ask now before we go ahead. So we'll just address it and go ahead. Do you have any questions from what we took yesterday?
Yes,
anybody? Yes, I'm with you.
Good morning.
Good morning. How are you?
Standby time. Is it just for television again?
And now, standby time. Some equipment can be put on standby. As you already know, your TV can be put on standby. If you put off your TV with your remote and it's still plugged, your TV goes off, but you still see that the red light is still on, which means it's on standby, such that once you just pick up your remote and put it on again, it comes on immediately. Now, some appliances don't have that function, and some people have TV and still don't put it on standby. So we should note the difference. Some people have their TV and they've never put their TV on standby because they understand the fact that even while on standby, it consumes power. So it's not that it's applicable just to TV alone, just that it is applicable. But your DSTV decoder also can be put on standby. Some appliances can be put on standby, not all appliances. I believe you understand my explanation, Mr. Biala. Is it clear?
Yes, I clear.
Okay, all right. Thank you very much. Is there any question again from yesterday? So that will just.
Sorry, in addition to that, yes, I hope everybody understood what power factor is. And Abiola, what those loads mean is that they are called vampire loads, or one of the words. So they absorb, consume power. Just to keep on, like your decoder, you see the light on, but you have switched it off. So it's like a vampire load. It consumes a little bit of power to keep on. So you can go ahead and explain.
Yeah, thank you very much, Mr. Felix, for that wonderful comment on the question. So today we'll continue from where we stopped. As yesterday, we looked at different appliances and how we can calculate their energy consumption based on their kilowatt rating and the time with which they are being used. And we treated some exercise yesterday in class, and I also gave a short exercise this morning, which a lot of people responded to, and this makes me know that you have an understanding of what we have done so far. So, however, I want you to not find we were using Excel, so it's faster and easier, but then beyond the Excel, I want you to understand what actually happened, in the sense that to get the power rating is given, and when you have the time, you just multiply it by your time. So power times time is the energy needed or the energy consumed, such that, because if you are writing an exam, you will most likely don't have an Excel sheet in front of you, so you need to understand the actual calculation or computation of these things. So you know, to get the total power is just the power for each of those appliances times the number of appliances that is available in that house, and you now further multiply it by the time of use or the period of which the energy was used, so that you can get the energy. So if we proceed, I believe my screen is up there on your screen and you can see it clearly. So I coined the exercise I gave this morning from this example here. However, on the exercise I gave, I noted that the refrigerator is 11. You have 11 refrigerator. Please, you can change it to 1. When you change it to 1, also still on this exercise, I realized that there was a small error on number 12. The total energy is 560. The daily energy in watt for item 12, which is the fan, is 560, not 640. And this will bring the total for this to 28748.10. 28748.10 to bring the total for this to 28748.10. So why I'm saying this is that we'll go ahead with this table, which you already have in your, on an Excel sheet, and would go further and calculate size for the component, or for the solar PV component that this load requirement can carry. So I've made 2 corrections to this table. The first is that you change the number of for refrigerator, the fridge, just change it to 1, not 11. And for the fan, there's a computation error on this slide. It should be 560. 560. So the total daily energy need for this will be 28748.1. So you can change it on your calculation sheet or Excel sheet, and I believe you get this answer if you effect those 2 corrections that I just mentioned. So let's move ahead from here and go to battery bank sizing. So today we'll be looking at sizing a battery bank. You know, the collection of your battery on your system, on your PV system, is called battery bank. It's your bank of battery. And well, I believe when you did system components, you'll be talking about strings of battery when you are connecting in parallel and in series. I believe Mr. Charles will have taken you that one extensively. However, to adequately size the battery bank, you must consider the following criteria. First, you need to consider the efficiency of the inverter. You need to consider the efficiency of the inverter. And I talked about the efficiency of the inverter yesterday, in that I said that a very good inverter will have an efficiency of around 90%. So you need to factor that the efficiency, the inverter has some conversion losses, from DC to AC conversion losses, that is up to 10% or more, depending on the inverter which you are working with. So for this, we'll factor it into what we have already calculated. And if I go back to that figure, which is 28748. Now, to add inverter efficiency to this, to add the inverter efficiency to what we are doing at the moment, we have to divide it by 0.9, which is the efficiency of the inverter. So I'll divide this by 0.9, and just so I can be sure you are following and participating, I'd like you to give me the answer to this, so I'll be sure we are actually computing this together. Are you with me, please? So 28741.1 divided by 0.9. Can you see my screen, Mr. Felix? Mr. Felix?
Yes, I can see your screen.
And you can see
And
what I'm
anyone else see
typing.
that?
You can see what I'm typing on the screen. Okay, thank you very much. So if you can see it, I would like you to supply the answer to this computation right away. Just unmute your mic and give me what you have. Is anybody saying? I didn't hear what you said. Your line was. Can you repeat it, please?
Can you hear me?
Yeah, I can hear you now.
Certainly, can you hear me?
Yeah, clearly now.
Okay. 31,942.3.
3. Okay, thank you very much.
31942.
Yeah, I've taken that. Thank you very much. So from what we have now, when we factor the inverter efficiency into this computation, as you can see, this took the energy requirement when you add the conversion losses of the inverter, took it to 31942.3. Okay, so let's proceed. So the depth of discharge. Now, again, I'll say at the point of taking components, I believe the whole concept of depth of discharge was explained to you extensively. So depth of discharge basically refers to the amount of energy you take out of your battery. How much or how deep, how much of energy did you take off your battery? How far did you discharge your battery? Let me put it that way. And for a good battery and for a good practice, let me put that word, you put your depth of discharge to a daily value of around 30%. Shouldn't be more than 30%. So what I'm saying in excess is you discharge your battery to 30% and you start your recharge cycle after discharging it to that. So in other words, always leave your battery at least 70% charge. The effect of this is it extends the battery life. It extends your battery life. It makes your battery healthy. It is not good to drain your battery by 100% every time. It is not a good practice, and I believe we all understand depth of discharge. And obviously, if I asked Mr. Eric to lecture us on depth of discharge, he has a lot of things to say about it. So we'll leave that to when it's time for Mr. Eric to comment. But let's just go ahead with our computation at this point, so we can move appreciably today. So like I said, basically the depth of discharge is the amount of energy you take out of the battery, is how far or how deep you discharge your battery. Take note, that is what depth of discharge is, and is different from state of charge. Depth of discharge is different from state of charge. The state of charge is the amount of energy that is present in your battery. So if your depth of discharge is 30%, then your state of charge will be 70%. So I want us to understand this concept and don't mix it up with each other. So we also look at the concept of system voltage, and the system voltage must be selected in accordance to your inverter input voltage, DC side. So for every inverter, you would see it's rated in In kVA, you see the power rating and you see the voltage rating on it. So it comes, typically you see a 1500 VA inverter, and you see on it 24 volts DC, 24 VDC, or 12 VDC, or 48 VDC. Now, in essence, like I said, since you have taken component, I want to believe all these have been made. They made you understand all this. So if your inverter is rated 12 volts, it means you can use minimum of one battery with that inverter. If you have 12 volts VC, minimum of one 12-volt battery. Now let me use the word 12-volt battery. Emphasis on 12-volt battery, because inverter is, because if you have two 6-volt battery, you can still use it on that system, and that has to do with the configuration of your connection, either you connect it in series or parallel. So let me ask this question before we go ahead. What is if I connect two 12-volt batteries in series, what will be my output voltage and my output ampere hour current, my output current? Who can tell me this? Quickly unmute your mic and let me have the solution. Mr. Abiola, I can see your answer raised. Is it for this question, or you had it raised all the while? So
regarding the voltage, we have
okay.
a 24 volt because series connection favors increase in voltage while the current remain constant.
Okay, thank you very much for that response. So if you have three 12-volt batteries connected in series, it means your output voltage will be 36 and your current remains at constant. So if it's a 12-volt 200 amps battery, it's going to be, your output voltage will reach 36 volts and your current will still remain at 200 ampere hour. So and if it's parallel, your voltage remains constant while the current will increase. So if it's a three 12-volt batteries connected in parallel, then you have your output voltage to remain at 12 volts. However, your output ampere hour would go up to 600. So these are the basics. I expected that by now you have full graphs of, so that, because we will be touching on this as we go ahead. So like I said, if I go back to our slide, we touched on depth of discharge, and I told you this, the amount of current you take out of the battery. Now I was on system voltage, so you can have inverters that are rated 12 volt DC, 24 volt DC, 48 volt DC, 96 volt DC. Now what this simply means is, per string of that inverter, that battery can use minimum. If you have a 24 volt DC battery, it means you need a minimum of two 12 volt batteries or four 6 volt batteries for that inverter to operate effectively. So it means that doesn't limit it that it's only two you can use. You can use 4 batteries with it, you can use 8 batteries with that inverter. But however, your configuration means per string you must have 24 volts for each of those strings. So if you have 8 batteries and you want to use it on 24 volt VDC battery, it means you have 4 strings of 2 batteries each connected in series, which means the output of each will be 24. Then you now parallel it, which still keeps the voltage at 24, which is still the operating voltage of the inverter. So if you have a 48 volt DC VDC inverter, it can be 5 kVA 48 VDC, it can be 3.5 kVA 48 VDC. Whatever it is, what it simply means that the minimum battery requirement for that inverter must add up to 48 volt VDC. So if you are using 12 volt batteries, it means you need minimum of 4 12 volt battery connected in one single series string. So that doesn't limit it that it's just a string. You can use 4, 5 strings on it. Just make sure that your configuration is following the 48 volt configuration. So imagine for a 48 volt DC batteries and you are using a 2 volt battery, 1500 ampere hour. This means you need 6 of those, you need 12 of those 2 volt batteries to add up to 48. So I just want us to have an understanding of the VDC of inverters, because eventually this will make up our system voltage. It will make up our system voltage and we really need to have an understanding of what this simply means. So, like I said, if you have a 3.5 kV inverter that is 24 volts, and it means you need minimum of 2 batteries connected in series, it doesn't still limit it to the fact that you cannot use 4 or 6 batteries depending on what you calculate. So let's go ahead with our sizing. I just chip that in because by the time we get there, it will serve as conviction for you. So system voltage, for our purpose, we assume, so for this calculation we are doing, we assume a system voltage of 48. This means that you will need minimum of 4 units of 12 volt battery. I have explained that. And for our Nigerian market, it is easier for you to see a 12 volt 200 ampere hour battery or a 12 volt 100 ampere hour battery than other configuration or specification of batteries. So deciding the system voltage, first, when you are designing, you also need to decide your system voltage. However, there are some rules that will guide your selection of system voltage. If you have a high energy demand that calls for powerful solar array, the current running through the charge controller can be very high. Then it is better to set up the system voltage, to step up your system voltage and reduce the charging current and the cost of the charge controller. So there's a table. If you look at this table, it gives us an idea of, or a range basically, of what the system voltage should look like. So if your total daily demand is around 0 to 4 kilowatt hour, so your peak power and your peak power per minute is 0 to 1 kilowatt, then you can limit your system voltage to just 12 volts. That is a small system and your energy requirement is very low. But when you are working in the range of 2 to 6 kilowatt hour per day, then your system voltage can be at 24. When you're working with a daily energy requirement or daily energy consumption of 4 to 12 kilowatt hour per day, then it is advisable now you take up your system voltage to minimum of 48 volts. Now, if you are working with anything from 8 kilowatt hour above per day, then you would want to use nothing less than 60 VDC. You want to make 60 VDC your system voltage. However, you can have a 96 volt DC system, you can have a 120 volt DC system, you can have 180 or 196 volt DC system. So what this simply means, as I would explain further so you can have a better grasp of this, is this determines even the choice of your component. This determines the number of components you will be using. So in sizing the battery, it is important to install one large enough to operate the appliance for at least 24 hours without recharging. So now you need to install a battery your battery bank needs to be able to take care of your system for at least a day before you are able to recharge. So it means you need to have enough battery to charge your system very well. Because not having enough battery means you have to imagine you didn't size properly and you have to recharge your battery twice a day to meet up your energy requirements. That is not so good. You kill the battery faster. So in climates that have long period of cloudy weather, a larger battery bank may be required here because there is no enough sun to recharge the battery daily. But then when you size your system such that whatever is used up in a day can be replenished by the sun that comes out in that same day, then it will make the system operate smoothly. When buying a battery, the voltage and the ampere hour rating must be known. I explained that. It is very important whether you are working with a 12 volt 200 amp battery or 12 volt 100 amp battery. For solar on system, the voltage will usually be 12, 24 or 48. Basically, our system voltage hovers around 12, 24 and 40. There are 36 volt system too. It's not like that is not as if it's not possible. So the capacity of your battery will depend on the energy requirement of your appliances. Manufacturers rate their batteries in ampere hour and not watt hour. So let's go ahead. All energy requirement calculated above are stored in the battery. So our energy requirement here is 31,942. They are stored in the battery. So you need a battery that can give 31,942 watt-hour per day. That is what the size of your battery bank should be. However, by the time we factor in days of autonomy, by the time we factor in depth of discharge, then we will see that our requirements will also go higher. So let's continue with our computation. So all energy requirement calculated above must be stored in the battery. The battery will supply the energy when needed. Follow these steps to determine the battery bank capacity. Determine the daily energy requirement of the load in your system. Taking our example of a 2-bedroom flat, we exclude heavy load. So now let's work with this same example that I gave us earlier. So I want to believe, let me know, we are going to take away heavy appliances, that is air conditioners, microwave, electric kettle, electric iron, and water heater. Let us do that now. From our calculations, we'll take away heavy appliances. We'll take away heavy appliances. So I believe you have an Excel sheet on your screen, which is the same Excel sheet that we worked on. And I will take away now air conditioners, take away microwave, kettle, electric iron. I'll take away the heavy appliances. I'll take away the heavy appliances. I've taken away air conditioner, microwave, electric kettle, iron, and water heater. So if I do this, it takes our energy requirement, our daily energy requirement. It takes it. So just follow this example that I have on the screen. It takes our daily energy requirement to 5498. 5498.10. So our daily energy requirement is 5498. Point. $549.10. So if you factor the inverter efficiency into that, Mr. Chigozie, I can see your hand is raised. Do you have a question? Kindly go ahead. And Mr. Felix too.
I thought electric hair dryer is a appliance.
What's that?
Electric hair dryer.
Electric hair dryer. As you can see, the consumption is around 250 watts. So we can leave it. Let's leave it there, unlike those that are about 1,000. So let's work with it. Just get the understanding. But for the purpose, if you want us to take it out, we can also take it out. But then we can also leave it if we want to. So if I take it out, it leaves us at 5448.10. It leaves us at 5448.10. So I want you to go ahead. Our daily energy requirement now is 5448.10. So I want you to go ahead to factor in the inverter efficiency we talked about earlier. So if you are doing that, now, so for here now, we have 5448. So what do you have? You can just tell me already.
6053.4.
Six what?
6053.4.
Okay, I want to believe everybody, we have the same answer. 5448. 1 divided by 0.9. So 6053.4, that is what I have here also. So that is the first thing we'll do. If we go ahead now, and we have factored in, according to this, our E daily now is our daily energy requirement is our E daily, and in our case is 5488.1 divided by 0.9. This is the energy demand which has to be supplied by the battery. And so if I see from this slide, it's a separate example. However, I want us to follow clearly. That is why I'm also working along with a separate example for us. So now we'll divide this value by the depth of discharge of the battery. So usually, like I said, for a good system, you keep your depth of discharge at 30%. But in practice, you see people putting their depth of discharge at 50. And thank God for lithium ion, which is a new battery technology, and I believe you have discussed that also. You can deep discharge lithium ion, and even from the specification sheet, you see on that lithium ion specification sheet that you can keep your depth of discharge up to 98%. You can take out 98% out of your battery, and it will still have a lot, because they have higher number of cycles. So it will still have a lot of cycles with you, even despite the fact that you keep your depth of discharge as high as 98%. However, for lead acid batteries, for AGM batteries, for gel batteries, we keep it at 30%. So for the purpose of our computation this morning, I'll put the depth of discharge at 30%, which is the ideal, or what is a very good practice. However, I can give us another value for depth of discharge for our assignment or presentation, just so you know the implication of depth of discharge. The higher your depth of discharge, the higher the number, and the lower your depth of discharge, the higher the number of batteries you have in your battery bank. However, let us continue. So you divide by 30% depth of discharge. So if we take our computation again, 6042 divided by 0.3 divided by 0.3. If you do that, if you divide our 6053, so you divide by DOD, depth of discharge. Our depth of discharge is 30%. So invariably, what we are saying is 6053 times 4 divided by 0.3. So you can give me the answer if you have it already.
20178.1.
So you have 20178.1. Thank you very much. So it has taken our energy requirement to 20178.1. So still on that, you divide this value by the depth of discharge of the battery to determine the required battery energy capacity. So what you require is a battery bank that can give an energy, a daily energy now in this case, of 20178.1 watt hours. So the lifetime of the battery is shortened when discharge 100% every day. Like I say, you don't discharge it every day, you shorten the lifespan. The lifespan is like when you take 50% out of your battery, you increase the number of cycles. So in order to reach an acceptable battery lifespan, we choose a DOD of no more than 30%. A good quality depth deep cycle battery can last 1,300 cycles in this mode of operation. So usually the life cycle of batteries batteries have around 400 number of cycles. But then when you have a DOD of 30%, you increase the number of cycles to around 1,300. But if your depth of discharge is 100%, that means your number of cycles is right there at 400. So a depth of discharge of 30% means that 8318 can only make up 30% of the battery capacity. This simply means that from our calculation now, we have 2178 is what we required for our battery to work. However, our depth of discharge, or what we need, is 6053. So if you look at the illustration on the screen, it simply means that we have worked with a depth of discharge of 30%, and the total energy requirement is 2178 for us, in this case 0.1. And where you have 30% up there, for us it will be 6053, and for where you have 70%, it will be 14124 watt hour. So simply, I believe we have an understanding of what is on the screen up to this particular position. And please, again, I say, if you have any question whatsoever, kindly ask so that I will re-explain it for us to understand, because the only reason why we are here is so that we can have full understanding of what we are doing. So Mr. Chikuze, go ahead with your question. I understand.
Okay, thank you very much, Tunde. When we are calculating the load, the total energy consumption, and all the appliances, in our previous Excel sheets, we have 6 hours for AC, but we didn't put into consideration of the surge, as you told us, because AC, refrigerator, they will have a surge of let's go times 7 times 0.5 seconds.
Yeah,
so
that's.
I was thinking.
Yeah.
Okay.
I understand your question now. So, like I explained yesterday, if you are sizing for AC alone, you would have to factor the surge capacity of this current into it. So, but now you can see from this system basically that there are other appliances, and there is what is called also demand factor, which means that at this, all your appliances can never be on at the same time. If you understand what I mean, there is no way everything will come on at the same time. That all the light in your house, all your AC, all your kettle, all your fridge will be working at the same time. It is not possible. So that is why you can, at this point, leave out the surge capacity, because there are a lot of other appliances that will make up total energy requirement, which will also means that, if our AC now is 1,200 watts, and the surge capacity for just 5 seconds, 0.5 seconds, not even 5 seconds, that is half of the seconds, is 2.5, 2.5 times its power. So it means our AC will go to about times 3 is 2.4, so about 3,000 watts just for 0.5 seconds. And like I explained yesterday, most inverters in the market they already have that such capacity specification, which means that they will tell you that this inverter is rated as 5 kVA, and it can take a such capacity of up to 10 kVA, of 8 kVA for 2 seconds, 6 kVA for 5 seconds. It is rated that way. So those specifications will take care of those surge capacity, such that it will reduce your daily load requirement. Because if you have a very high daily load requirement, it simply means that you'll be buying more batteries, you'll be buying more panels, and you'll be using bigger inverters. If you understand what I mean. So but if all you are just sizing for is just an inverter that will take your AC alone, then you need to factor in this, like I've explained, you need to factor the surge current into it, such that if you are just going to run two ACs at the same time, which is 2,400 watts, let's put it like that, and that is the only thing you are sizing for, that is the only load you have. So you won't go and buy an inverter of 3,000 watts or 2,400 exactly. You would want to factor the surge current of these inverters into your daily load requirement. Mr. Chigozie, I believe at this point I've been able to answer your question.
Yes, sir. Yes, sir. Yes.
Okay, thank you very much. Does any other person have a question at this point before we go ahead? Mr. Olufemi, kindly go ahead and ask your question.
Okay. Sir, I want to know how we get this 2 to 5 years depending on the battery quality. Is it from this calculation or is it because we are doing 30% depth of discharge?
Now it's because we are doing 30% depth of discharge. It helps the battery quality. So if you do 30% and it gives you 2 to 5 years, it simply means if you are doing 100%, it's going to be definitely less than that. You understand?
Okay.
Yeah.
Okay.
So again, I'm happy we are asking questions at this point. So if you have a question, now it is time for you to answer, so we can all have a better understanding of what we are taking at this point. Any other question, please, before we go ahead? Is there anybody that have a question? So I want to take it that up until this moment, you understand everything we have explained in terms of system sizing, because basically we have looked at how to calculate your daily energy requirement, and we have factored in the inverter efficiency into it, which is conversion losses, and we have also looked at the concept of depth of discharge, which will also give you the amount of energy required from your battery bank. And so we'll go ahead from there at this point. This simply means that so we are working with this figure here, so we don't mix it. It's the same thing if you use the figure on the slide, so you can on your own also take note of those figures so you cross check. However, we'll do a classwork also, so that I would be sure that we understand what is going on. So for 2178.14 watt hours, the next thing we are going to do now is to divide the required battery energy capacity by the system voltage to determine the battery capacity in ampere hour. So now, like I said earlier, we need I explained system voltage to us, and we would also get better understanding as we go ahead. So now, if we look at the table I showed you for system voltage, so take note of our energy requirement at 20,000 here, and from the table, if your daily energy requirement is more than 8, you are advised to use 60. You understand? And I've said, if you look at this same slide on the third to the last line, I say for solar PV system in ohms, the voltage will usually be 12, 24, or 48. So I would just say let us work with a 48 volt DC system voltage here. So we'll select a 48 volt system voltage for our calculation, and this will now give us the battery bank capacity that we require, to give us the battery bank capacity that we require. So if you go ahead now and divide our answer, which is 2178, by the system voltage, which is 48. In our case, we are choosing 48. So I'll just say also divided by the system voltage. Now, I'll use the word selected voltage. System voltage. Here, we divide by the selected system voltage. So we'll have now 2178.1 divided by 48 volt. So, like I said, if 2178.1 divided by 48 volt. So I have on my screen here 420.
420.8.
420.37.4. You just put it out 420 right there, and the unit is ampere hour. So let's look at this critically. It simply means that here that our battery capacity that we need for this to work is 420 ampere hour battery. Now, the 420 ampere hour battery here. So now, let's now come back home. When I say come back home, let's come back to our Nigerian market. Let's come back to our Nigerian market. And in our market, what is, I say, if you are looking for a 12 volt 200 amps battery and you step into a battery market, it won't take you up to a minute before you start seeing different brands and sizes of 12 volt 200 Ah battery. If you are looking for 12 volt 100 Ah battery, it might not take that much. It might also take that much time or more. So what this simply means is that in our Nigerian market, we have a lot of 12 volt 200 Ah battery. So I would say let's work with what we have in our market. And based on our calculation, our requirement now is we need a 420.3 ampere hour battery capacity. Now let's follow this critically. Our battery is what? Which means how many string of battery do we need to make up 420 ampere hour? Can anybody suggest? So if you divide this by the ampere hour of the battery you have in the market, so let's say we are working off with 200 ampere hour battery. Now it means you need 3 strings of 200 ampere hour battery here to make up 420. Because if you do 2, that is 400, and there will be a lag in it means you are not able to supply what you require. But when you use 3 200 ampere hour battery, 3 strings now, because note that each of our string is 48 volt DC. So we are working with a 48 volt DC inverter, which means for every string you need 4 batteries. You understand? And from this example now, which is also not asked of place, the battery bank has a system voltage of 48 and a required capacity of 579. If you look at the slide, also 420, it's fall within the same range. So for 579, it means you also need 200 Ah times 3 to make up this. And this simply means for 48 volt system voltage, you need an input of 4 batteries to make up that. So it means your first 200 Ah output current is what? We are connected in series now. Your first output from the first string is 200 ampere hour. From the second string, another 200 ampere hour. From the third string, another 200 ampere hour, because they are connected in series. Then you now do a parallel connection of the 3 string of battery. So now, when you connect in parallel or series, that is a string. And you can see on this screen, you have 3 strings of batteries here, which the output gives us 200 Ah. The first one, which is the first line of 4 batteries, if you measure the output, you can see they are connected in series. So it means the output of the first one is going to be what? 48 volt, 200 ampere hour. I believe nobody is confused. The second string also is 48 volt, 200 ampere hour. And the third string is 48 volt, 200 ampere hour, because we are working with a 48 volt DC system. So this will in turn now be connected in parallel to give us a 48 volt, 600 ampere hour battery connection. Now, like I said, for our value here now, if you look at the value we have 420. And in our Nigerian market also, let me put it this way, if you are, let me not use the word smart, you can also help to your client to reduce the number of batteries here based on our 420. And rather than go for a 200 ampere hour battery, you go for a 220 ampere hour battery. We also have 220 ampere hour battery in the Nigerian market. Just that you might check for a little while. We have 205, we have 210, and I've seen 220. So rather than go for 3 strings, I can do 2 strings of 220 ampere hour battery, which simply means that I'll have 8 batteries rather than have 12 batteries. And each of them will be 12 volt, 220 ampere hour. And this is possible because my battery requirement is 420. For the battery requirement on the screen, that is not possible because it's 579. That is almost 600 already. So for 420, to cut off the extra string, you can do a 220 or a 210 ampere hour battery. So if you do 220, that means you'll be having your system voltage will be 48 volt DC, 220 ampere hour, 48 volts DC, then 220 plus 220 is 440 ampere hour. That is your total requirement, which is also higher than what we need is 420 and we have 440, which means you can cover your daily energy requirement from your battery. Let me pause here so that you can take this in, and I'll be sure you understand what I've explained so far. So now, if you have any question, let me know now. From this, what we did is simple. The first thing we did, we took our daily energy requirement that we calculated from the table and we divided it by the conversion loss of the inverter. That is the inverter efficiency of 90. We took it up to about 5,000 or 6,000. I'm not on the screen now, but you understand what I'm saying. Then we now further divided it. I can see your hand out, Mr. Bell, I'm coming, by your depth of discharge. After dividing further by depth of discharge, we now looked at the system voltage we are working at, because when you divide by your depth of discharge, you still have your calculation in watt hour. So and for the formula of power is P equals to voltage times current, and you have in watt hour. So if we divide by the system voltage of 48 volts, so our rating will now be in ampere hour, which means that for our calculation we have 420 ampere hours of battery. And I give us a different variant of how you can also help reduce, because it's close to 400. If you use 400, 2 strings of 200 ampere hour batteries for this, it will not cover your daily energy requirements. However, there's also the possibility of you getting a 220 ampere hour battery in our market, because I know it is available, or a 210 ampere hour battery. And by the time you get that, it will help you reduce the number of strings. However, for the example on the screen, which their battery capacity requirement is 579, all they need is to make it up to 600 and use 3 strings of battery. So now I will want to tweak this calculation further by telling you now to go ahead and calculate for a 24 volt system voltage for this particular example that we are doing for our 420. Now, what brought us to 420 is that we divided by 48 volts. So rather than divide by 48 volts, now divide your 2178 by 24 volt system. Let's have your answer. So if you have a question, Mr. Biola, your hand was raised the other time. Do you want to ask the question? You have clarity based on my explanation.
Perhaps I could chip in just a
Yeah,
bit
Mr.
here
Eric,
at
go
this
ahead,
point.
please. Yeah.
And this is interesting here, that what we are seeing is a case of good practice, or even best practice, that we always want to cover our load, and yet at the same time it's good for us to realize that when we are looking at these calculations, in order to, as I said, cover our load, really what it is to cover our load without exceeding a depth of discharge of 30%. It doesn't mean that the lights will shut off if we were to, say, use an 8 battery string as opposed to a 12 battery string, but or not string, but a collection, or let's say bank, to use the proper term. But if you went with 8 batteries, when really what the system is requiring by these calculations is 12 batteries, you would be going in just a little bit below that 30% depth of discharge. So that by this arrangement here, the demand being calculated to 420 amp hours, and we can see with our 200 amp hour batteries, we could almost cover with 8 batteries. That's at 30% depth of discharge. If we do that, if we decided, we can get away with 8 batteries, what we're saying in essence is not that the system won't work, but that the system will be discharged, if used as designed, to maybe 33% or 34%. If you decide to say, well, we're going to go with best practice and get 12 batteries in there, you can then run those numbers again based on that 600 amp hours. And if you take your calculations and run them backwards, you would find that the depth of discharge is then maybe 22 or 23%, which translates into a longer battery life. So you've purchased 12 batteries, but the battery bank might last, say, 5 years as opposed to 4 years. But it's not a black and white calculation. We have some discretion here, including the setting of 30% depth of discharge. When we have resources to do a good design system, we tend towards 30%, 33%, 40%, very rarely going beyond 50%. But there are always pressures with the client to try to get more capacity out of the system for less investment. So there's a lot of pressure to, say, go with, in a situation like this, to go with an 8 battery bank system. And oftentimes the best thing to do is to put this in the hands of the client and say, well, by our standards, this system would require 12 batteries. If we go with 8 batteries, the system will work perfectly well, but we'll be cutting the battery life overall by perhaps a year. But on the other hand, we're saving 1/3 of the initial battery investment. And this kind of trade-off is made all of the time. Now, in the market, sometimes you can get some 225 AHs or 205 AHs, and that's a good direction to go if it is a price competitive sort of situation. And when you're looking in the marketplace, and as was indicated by our instructor, you can't be a minute in this marketplace without seeing that there are all sorts of different options there. And what you want to do is, say if it were all within 12-volt batteries, you want to run how many NIDA are you getting per amp hour, or rather, how many amp hours are you getting per 1,000 NIDA of investment? And assuming that the reputation of both batteries is the same, you just go with your best investment. You don't really want to use the math as the driver of getting a little teeny bit better, a bigger battery, unless it is at the same price. You don't want to have to pay a premium for that, because that would be a false economy. And this number that led us to the 420 is something that we've arbitrarily set this up so that we would arrive to that number of 420 by us arbitrarily choosing that we want the battery bank to have a depth of discharge of no more than 30%. If, for example, another instructor came and said, well, you know, I've always learned to use 33% for my depth of discharge, 1/3 of the total capacity. In that situation, if the numbers were run, you would come to a calculation at the end of the day where it would be 370 amp hours that are required, and 8 batteries would meet the need perfectly well. So we want to know the mechanics of this, and we want to adhere as much as possible towards best practice, but we don't want to be blindly following these numbers as if they were somehow you know, black and white, that if you're, you know, just a little bit over, it's going to mean one thing, and if you're a little bit under, it's going to mean something completely different. This is all on a gradation. Now, the last thing I would add to this is that why do we say 30% then, as opposed to 50%, or as opposed to 70%? And it really is a very, very subtle situation at which point on that curve that you decide you don't want to do any more depth of discharge. And I would encourage us to think in the following terms, that if you are around the 30% depth of discharge level, you're getting a very good and long return on your battery. And if you go deeper, as we all are intuitively aware, if you discharge more, you are going to shorten the battery life. But here's the tidbit that is often not spoken, and that is the following. When you are doing a depth of discharge of greater than 50%, the curve is steep, and that steepness of the curve can be translated in the following way, that if you go 1% deeper in depth of discharge, you will lose more than 1% of the battery life. So, for example, if somebody says to you, well, this is going to cost you 1% more, but it will last 1% longer, you're going to say, well, that's roughly the same. Or if you, and indeed, we've got some curves here, and we can see that these are not straight line relationships. So at the point where you are starting to get beyond 50% depth of discharge for your battery, what's happening is you decide to go from 50% to 51% depth of discharge. You're going to reduce not 1% of battery life, but you will reduce 1.5% or 2% of battery life, such to the point when you get down towards 80% depth of discharge, every percent more is going to result in 2 or 3% loss of life, every percent more in terms of depth of discharge. So you're only getting 1% more power, or rather energy, but you're sacrificing 2% or 3% of life. And of course, that trade-off becomes a very painful one. However, at the level of 30, the arguments are fairly balanced. If you decide to say, well, I'm going to go 1% or 2% more to be able to fit my battery bank into the parameters, in this case here, deciding perhaps to go to fit this as an 8 battery system, you're probably making what is going to be an economically neutral decision in terms of the battery life. And this is not something that all of our technicians can handle in terms of the calculations. But if we can manage an understanding of those curves, and we can understand this relationship of a little bit longer life comes from a little bit less depth of discharge, and that relationship changes over the range between 20% depth of discharge and 80% depth of discharge, we can make a nuanced decision about this battery bank that is placed before us on the screen share right now, about do we invest in 12 batteries or do we invest in 8 batteries? Thank you for giving me a chance there to broaden that discussion.
Yeah. Thank you very, very much, Mr. Eric, for taking us on the implication of depth of discharge and the possible scenarios. Thank you so much. So basically, I believe we will have an understanding of the effect. Now, there is a trade-off of either, like I was explaining, going for a 210 AH battery or still using the 200 ampere hour battery and going further on your depth of discharge. Now, because we have set our depth of discharge to 30%, as Mr. Eric has explained, doesn't mean that the system won't work. It simply means that if we stick to 8 batteries rather than 12 batteries, it means we have increased our depth of discharge to about 30 something, or if it tends to 40. Then now, if we further now say, which is what you might meet, except for the fact that if you come across clients that have the resources available and are keen on quality of their system, they would go by your recommendation and take 30% depth of discharge. But most times in practice, or what we have obtainable in Nigeria here, is everybody wants to cut down the budget and they want you to use the lowest possible budget. And somebody will just ask you straight up, can't I use 4 batteries? I only have money for 4 batteries. Now, this simply means
this
that
really gets to be a hard argument, doesn't it?
Yes. So this simply means that the system will work. Yes, it's a 48 volt system, which means you need a minimum of 4 batteries for that inverter to operate. However, the implication of this is you'll be deep discharging those batteries to about 80% or 70% depth of discharge for using just 4 batteries. And this will reduce the battery life extensively, compared to when you are 30% depth of discharge. So it's not a white paper thing that has to be 30%. In practice, you would hear, I want to power this, I want to power this, I want to power this. You give option 20 batteries. They tell you, see, my brother, somebody have agreed to do this for 4 batteries. Can you do it or not? Fine. Now you have to leave it at the desk of the client and explain the implication as an engineer that you are, or as an installer that have gone through this course, that see, it will work with 4 battery. However, these are the implications. It will take your depth of discharge to about 90% or 100%, as the case may be. And it will now mean that you have to replace your battery very soon. So do your own part to explain the possible scenarios of whatever solution you are providing or administering to your client at that point in time. So I believe we will now have a good understanding of even depth of discharge as a concept. So deep discharge your battery, like I said, the lower your depth of discharge, the more batteries you use, the higher your battery life also. The higher your depth of discharge, you use little batteries, but you have less battery life, which I believe from my explanation and Mr. Eric's explanation, you should have a better understanding of what it is at this time. So I'll go ahead and ask us to work with a 24-volt system. Let's say our calculation so far, rather than choose a 48-volt system, we chose a 24-volt system. What will be your requirement for battery? Has anybody done that? I expect, okay, Mr. Chigoze, go ahead. I expect that we quickly do that as the explanation was ongoing. So go ahead, what do you have?
Yeah, I have, if I'm using 12 volts, 200 ampere hour, I'm going to use 10 batteries. That is 5 streams. Each stream
12,
with 2.
wait, 12 volt or 24 volts now?
If I'm going to use 24-volt system, can you hear me?
I'm with you.
If I'm going to 24-volt system, I'm going to pick 12 volts, 200 ampere hour battery. So
Okay.
my system will contain 10 batteries, which will have 5 streams. It will give me 24 volts, 1000 ampere hour. Or if I'm going to make it economical, I will prefer 12 volts, 220 ampere hour. Then my system will have 8 batteries, which will give me 4 streams. Each stream 2 batteries, which will be 240, 24 volt and 88 ampere hour.
Okay, so again, so from the calculation now, the figure for your battery capacity is 840.
840.
Which is why 0.75, which is why you chose a 5-string battery of two batteries each. So now, from the explanation that we have given so far, especially by Mr. Eric, what will be the implication of using 8 batteries? That is 2 batteries per string or 4 each. What will be the implication of that? Will the system work? Will it not work? And what will it affect?
The system will work, but our depth of discharge will have an effect on our depth of discharge. It will be more than that.
What effect, actually?
It will be more than 30% of our particular depth of discharge.
Okay, that's exactly what I wanted to know. It takes the depth of discharge up. So again, is there anybody that doesn't understand so far what we are talking about or where we have gotten to? Please let us ask now.
Let us throw a question to the assembled group here,
Okay.
and keeping the slide of the 48-volt system on the table, even as we're contemplating Chigoze's calculation of 10 batteries being required rather than 12 batteries being required for the 24-volt system. It's not that the 24-volt system is more efficient, it's just that it could be closer to meeting the parameters the required by this 420 amp hours. So it is an interesting kind of play on how much flexibility you have in designing your battery bank with those parameters. Interestingly enough, if we were working with this as a 12-volt system, and you may already be planning to mention this, Tundi, so forgive me if I jump it.
No, it's fine.
If it was a 12-volt system, you could probably design the system to work with 9 batteries because you have complete flexibility in terms of the how you lay it out, or you're going to be laying it out as parallel connections. But let me ask the group, why would, in the 48-volt system, which is probably a better indicator of what we'd be facing in the market today, we're working towards higher voltages. Why, let's say the client came to you and proposed, I can't afford the 12 batteries. And you say that it'll work fine with 8 batteries. But somebody else has told me that we can do it. We can do it with 4 batteries. Apart from the depth of discharge, why would you not want to go to 4 batteries? A single string of 4 batteries for a situation like this. Who could among us could say, and I can see that we have easily 15 people in the room. Why might you not want to have a single string providing for your load? Go ahead. I see a hand raised.
Yeah, thank you, sir. I think for a good, thorough and quality work, the consultant should stick to the specifications that you have given to your client, because in future, if there's any problem, as we know in Nigeria today, the consumer is not likely to restrict himself or herself or themselves to the specifications on the load. They are likely to use more than the load in future than has been specified. And so it is very necessary for us to give this ample room for enough batteries in the bank, so that plus or minus the work that you have executed will have a lot of quality. I have an experience like that of a colleague that has a farm somewhere in Ogun State, and I was there, and he told me that the solar PV system that was installed for him packed up, and that was one of the things that sparked up my interest in this line of energy power, and the farm could not use that solar PV for a long time. He was looking for appropriate engineer to come and do a correction for him, which he has not seen. Thank you, sir.
Yeah, that's a general answer and a crafty one, I will acknowledge. But it's and it speaks to the fact that if given the resources, and if we have a client who wants to get first quality, we should always talk in terms of ample resources, precisely because loads do tend to creep upwards rather than creep downwards. But there's a very specific technical reason that makes the life of the installer and the technician that services the system much easier if you don't operate with a single string. And so what is the reason that, when possible, for multiple battery bank systems, that you would want to configure it in 2 strings at a minimum? Who could tell us what that answer might be? Any thoughts? Go ahead.
Yeah,
Mr.
I feel to maintain the required system voltage and the amperage required by the load.
Now, I'm not talking about the voltage or the amperage hours or the amperages in question, but just in terms of how you would lay out a system electrically. And what it comes down to is that, imagine that you've got 8 batteries or 12 batteries that you're dealing with, or versus 4 batteries if you were to go with a single string. When you have situations with multiple batteries, there will be, on occasion, difficulties develop with one of the batteries. But if you've got a single string for your system, you have to take down the whole system in order to check even one of the batteries. But in the case of, and let's say here that our best practice would be a 12 battery system here for this 48 volt that instructor Tunde or Professor Tunde has laid out for us. If we were with a single string, however, and there would be clients that would push for that, and they will have said, but I spoke to another technician that said we can do it with 4. But in that case of a 4 battery string, if you need to service one of the batteries, or you have one of the batteries go bad and needs to be replaced, you don't even have the option of leaving the system up and running. You have to shut the system down because it won't work with 3. But in the case of 8, you could have one battery on one string go bad and one battery on the other string go bad, and then you could take one of the good ones from the first string and put it into the second string, and you could still cobble together a working system that would leave the client with power, at least during that period where you then went and changed out the batteries. But when you're on a single strand, you really are very, very dependent on every one of those batteries working perfectly all the time, which is not consistent with reality. And you're far better off having 2 strings so that even though as a long-term solution that's not ideal, you can leave the system functioning while you replace batteries or even just test out batteries. Oftentimes, you have a battery that may seem to be suspect. Well, you need to take it back and give it a full charge and see how it handles a discharge or the load of a battery test. You can even do this work of fooling around with some of the batteries on the site and still leave the system functioning rather than taking the system down for any length of time while you're doing this work. And so this is something also to use in your favor and to avoid being pushed too far in terms of cutting the batteries in the battery bank. We've got reasons for depth of discharge to keep the system bigger, but you have relentless pressure from the clients to make the system smaller. And there is definitely a limit beyond which you want to go. And for this system that's up on the screen share, 8 batteries truly is the minimum that will provide us with a good, stable system. Even though if you went with a 4 battery system, that's if an 8 battery system, and I'm looking at these numbers, 420 amp hours was the requirement. If we cheated, as we might say, and went with 400 amp hours, remember, we're only cheating about 5%, and that's 5% of 30%. And so it's going to mean a depth of discharge of, at the end of the day, about 31%. If you went with a 4 battery string, that would mean 62%. The system would be working, but it wouldn't allow it to be serviced as easily as the 8 battery system. So you have a greater depth of discharge, and you have a system that is harder to service. And you put those 2 things together, and you've got some compelling arguments for going for at least the 8 battery system. I'll pass the chalk back to you, Professor Tunde.
Thank you very much, Professor Eric. Mr. Eric is actually the prof here. So let's go ahead. I believe Mr. Eric have even made us to understand this. So he has made it so very simple for us to comprehend and understand. So I'll go ahead and I'll have us try it with now still using a 48 volt system, but now we'll be looking at the fact that what you have available in the market is the 100 Ah battery, 12 volt 100 Ah battery. So kindly do your computation and let me know what you would use for a 100 ampere hour battery. At 420 battery capacity. So kindly, if you are done, please unmute your mic. Let me have your answer already.
I didn't get your question, sir.
So now, all the while we have been working with 12 volts 200 ampere hour battery. So let's say you now get to the market and what you have available is a 12 volt 100 ampere hour battery. And all you have is a 12 volt 100 ampere hour battery. What will be the situation?
Or more likely, because you have the choice between 12 100 amp hour and 12 200 amp hour. But let's say your best price in the market, a very good price on 100 amp hour batteries, and so that we are inclined towards that. And for those that think that they're being clever by saying it's only going to just mean 24 batteries as opposed to 12. You might find that the math is more interesting than that.
So if you have the possible solution,
5 strings of 100
Mr.
You have 5 strings.
I will
If you are
increase
using,
of a 48.
if you are using 100 ampere hour, you have 5 strings.
5 strings of how many
100.
batteries?
4 batteries.
What's your total number of batteries?
Total number of batteries is 20.
Okay, 20 batteries. Yeah. Any other person with any other suggestion? Mr. Chigoze, kindly speak.
If we are using 12 volts, 100 ampere hour battery,
Yeah.
when we are considering 24 volts, we are going to use 9 streams. Each stream
9.
contains.
Okay,
Yes,
when you
each
use
stream
24, okay. Okay, what if we work with 48?
Okay, if we work with 48,
Yeah.
we are going to use 5 streams.
Okay. So so far I believe it's just 2 or 3 people talking, and I don't know, others are not saying anything. I want to believe you have an understanding of what we have been saying so far. Mr. Charles, Cornell, kindly unmute your mic and let me know that you understand and you're following. Mayowa, Ajara, Mr. David, please unmute your mic. Let me know that we are all on the same page. Just to
good morning, sir.
Mr. Charles, good morning. Yeah.
I just want to put in my answer quickly for the 24 volt. Yes, sir.
Yes, your voice is on and off, so I don't know. What did you say?
I said,
I'm with you.
Keeping my answer for the 24 volt system using 12 volt 100 amp hour battery.
Okay.
Okay,
What's the answer?
I want to go. I want to use 24 batteries. That's 6 string.
You said for 100 ampere hour battery, your answer is
what? 6 strings. We'll be using 6 strings of batteries.
6 strings of battery. Okay.
Yes, 24 batteries altogether.
Okay. Thank you very much. Does anyone have a contract? Mr. Charles, I see your hand. Please go ahead.
Well, since we are going with 48 volts,
Okay.
we'll have to have 4 batteries per string, and if
Okay.
each so that means we have 48 and 100. So we need to have 5 strings to have 500 amp hours.
Okay.
So 5
Okay.
times 4 is 20.
Okay. Thank you very much. Your answer is also in line with what have already been said. It shows that you're also following. Who else? Mr. Dimka, yes, I've not heard your voice today. Are you with us today? Mr. Dimka. Ajara, are you with us? Are you following?
Sorry, I'm having network issue.
Okay, but are you following? Are you following?
Yes, I'm following.
Okay. Okay. I want to believe, Mr. Felix, you want to say something?
Yes, no, Hajara is Greco. She's Greco staff with us.
This Greco. Oh, okay.
Yes.
Okay. Thank you very much.
Along with Lydia. Yes.
Okay. Thank you very much for that. Mr. Ebuka, yes, I've not heard from you today. Are you following us? Do you have full understanding of what we have done so far? Mr. Ebuka. Okay. No response from him as well. So let's go ahead. Let's go.
This is very revealing to make these inquiries. I think it is very appropriate. It lets us know who is with us and who perhaps has drifted away. And I think that's sometimes necessary in circumstances.
Sorry, I'm here. I didn't follow up on yesterday class, so I'm finding it difficult to understand what is happening today, though. So I wasn't around in yesterday class, but Mr. Chukwuzi, due to it's my working colleagues, he's trying to explain some certain terms for me to get it here.
Okay, that's great. Please see Mr. Chigozie, and I believe Mr. Felix also posted a YouTube link of today's class, which I think there will also be that of yesterday's class too, so you can follow up on that.
Okay, sir. Okay.
Yeah. So, Colonel Kuvuki, are you with us today? Colonel, let me use Mr. Eric's word, drifted away.
The more appropriate term is ghosting, posting through.
Okay.
That's Adeola.
Okay, Adeola, okay. Are you with us today or you are ghosting through? Okay, no response. It means it's definitely not by his device at this time. Mr. Kola always has been with us. So. Mr. Raphael, Mr. Raphael, are you with us at this time? Mr. Raphael.
Yes.
Okay, do you understand everything we have been doing so far, or you have a question?
I'm getting a small understanding, but the problem, I don't know whether because I'm using a small phone, the board is not too clear. I can't see the writing.
Oh, okay. Okay, maybe because your screen is smaller. I think maybe well, the link, the video link is also there for you to follow up, and I believe by the time we share the slides also, you'll be able to zoom in on some of the calculations we are doing and get it. And finally, I'll ask Maiwa, are you with us today?
Yes, sir.
Maiwa, you understand what we have done so far?
Yes, sir. Yes.
Okay, so I've basically called on everybody. I guess Mr. David has been with us So let's continue. Let's continue. We have so far looked at the different ways we can play around with these calculations, and Mr. Eric has also engaged us on the possible implications of this, which is a very good one from Mr. Eric. So as an exercise, sorry, we are going to take a lot of exercise just so we understand perfectly what we are doing. And now, earlier we took out the air conditioner, the microwave, the electric iron, and the water heater, and the dryer, I guess. So what would be the required battery bank capacity if the air conditioner, microwave, electric iron, and water heater are connected back to the system? So now you need to go back to the Excel sheet from the beginning and add also the air conditioner, the microwave, the electric iron, and I think we can do this as an exercise right away for about 10-15 minutes. And what battery bank will be required to provide the room with electricity of 24 hours? That is still the same thing. So if the air conditioner iron are not included in the system, what will be the appropriate battery capacity? That is what we have been doing since morning. So now the exercise now is for you to now include back into this configuration the air conditioner, the electric iron, the microwave, and the electric kettle, and now do the calculation we've been doing since morning. It is an individual exercise. Because I want you to do it yourself, I want you to do it individually. I won't say it's a group exercise. Let us do it as an individual exercise. And this is 10:37, and at 10:50 we'll review our answer. So to make it easy, let's work with to make it uniform rather, let's work with 48 volt 200 ampere hour batteries. 48 volt 200 ampere hour batteries. So let's do it individually. It's an individual exercise at this point. I want to see what our solutions will be. So we are doing the exercise. Mr. Charles, go ahead, please. I can see your hand is raised. And Mr. David. Okay, Mr. Charles first. I'm listening.
I came in late.
Okay.
So I didn't have the original document that they used.
So the original document is the same with what I shared on the WhatsApp group this morning. And just that we did some little adjustment to that, which is that the refrigerator is now 1 instead of 11.
Okay.
Yeah, so okay, let's go ahead. Mr. David, have I answered your question?
I'll check that.
Okay, please, let's check. I would also see and repost it on the WhatsApp group so that we all be on the same.
Someone's hand is up. Okay, he has muted.
He muted, yeah.
Okay. All right, so go ahead.
So I'll share again the Excel sheet on the WhatsApp group just so we have it again, I guess, for those that did start with us. But now we need to all do this exercise now so that we would know, and as many that have left their device. So I've shared it on the WhatsApp group again. You can just pick it from there already. So you have it there on the WhatsApp group. Just that you need to do the calculation again for the total power Let me just do this as we speak. Let me also solve it along with you.
Sir, what is the battery specification, sir?
12 volts, 200 ampere hour. I use a 48 volt system.
Sir, can I go? Hello?
Mr. Chigese, what did you say? I said 12 volts, 200 ampere hour, and 48 volts VDC.
Can I tell what I got?
Hold on, let's wait for others. Just hold on. Mr. Femi, I see your answer raised. Do you have a question or?
I want to say my answer.
Okay, let's hold on. It seems most of us has finished, so I guess we can start turning in our answer. So Mr. Chigozie wanted to say his first. So just give me an answer. I think I'll just write them down here. So, Mr. Femi, what do you have for us?
I have the battery capacity is 2,218.2 ampere hour.
Okay. Okay.
We'll need 12 strings of battery. 12 strings of battery, making 48 batteries required.
12 strings. Okay.
Yes.
12 strings of batteries. Okay. Okay, thank you very much. Mr. Chigozie, go ahead with your answer. Thank you, Mr. Femi. I've noted it.
Oh, as using 48 volts system, my battery will be 2,958.95.
Are you 2,958.95?
Yes.
Okay.
Yes. Then I'll be using 15 streams, which will give me 15 streams. Each streams will have 4 batteries. That will give us 48 volts, 200 ampere. Then the total capacity will be 48 volts, 3,000 ampere hour.
Okay. Okay. So who is next? Mr. Femi, your hand is still up. Do you want to say something, or is from the other time?
It's from the other time.
Okay, sir. So who else wants to give us his or her answer? Should I just call everybody's name as they appear on my screen? And the first name of Mr. Charles Moby, your name is on my screen. Are you done? Can I have your answer now? Mr. Charles. Okay. Mr.
It would be good to say you don't have your answer yet, not no one.
Rather than not saying anything.
You don't have your answer yet. That's more proper.
Okay, so if you don't have your answer, just unmute your mic and say you don't have your answer yet. That's simple. So, Mr. Charles, do you have your answer for us now? The next, okay, Mr. Charles.
Not yet.
Okay, sir. The next question, Mayowa, do you have your answer yet? Mayowa.
Yes, I do. My battery capacity is 2218.2 ampere.
Okay.
I have number of strings will be 12, and the amount of batteries will be 48.
Okay. Thank you very much, Mayowa. The next person is Mr. David Omoni. You are next on my screen. Mr. David. David.
I'm not yet through, sir.
Okay. Mr. Raphael, are you able to see your screen and answer this question? Mr. Raphael, are you through?
No, sir.
Okay, Mr. Raphael is not through. Okay. Mr. Abiola, you are next on my list here.
I'm not sure yet.
Okay, Mr. Abiola is not also true. Mr. Ebuka, Mr. Chukwu Ebuka. Mr. Chukwu Ebuka.
I'm yet to figure it out, sir.
Oh, okay. Yeah, you mentioned the other time.
Yes, I'm yet to figure it out.
Mr. Dimka, are you able to give us your answer at this time?
Mr. Unfortunately, just like Mr. Ebuka, I'm also having challenges, sir.
Okay, sir. Cornell. Okay, sir. Cornell Kuwuki, are you able to give us your answer? I'm not sure it's right there, but it's device.
Sorry, I'm not through yet. Please. I'm not through yet, please.
Okay, that's good. Who else is there? Mr. Kola Ole Adeshina. Mr. Kola Ole, are you true?
Hello, sir. Hello, sir.
I'm with you, sir.
True.
Go ahead. Okay, let me have your answer, sir.
Yeah, from the data you gave us, The total power
Okay.
I have here is 11681.1, and then
11.
the
Okay.
681.1, and
Okay.
then the daily energy usage I have here is 28784.1.
Okay, sir. Okay.
And if I want to know the value or the inverter to be used, I have hello.
I'm with you. Just give me your battery
Yeah.
capacity, your total
Yes.
battery capacity.
Okay, my total battery capacity here is 106474.4.
Wow. Okay.
Yes, with a depth of the size of 30%. And
Okay.
I have, yes. Now I want to know the ampere hour. The ampere hour for that will be 2218.218.
Okay.
For
Okay. This
a
is your battery
battery,
capacity.
yes, yes.
Okay.
Using a 48 volts
System.
and
Okay.
200 ampere.
Okay.
Yes,
Yeah.
and that will give me about 11.09 strings. 11.09
But in reality, how many?
which sums to 12 strings of battery.
Okay. Okay.
Yes.
You have 12 strings. Okay. Thank you. I believe I've called everybody. Or if you have your answer now, can you unmute your mic and just go ahead?
I've sent that to your WhatsApp.
Okay. Thank you, sir, Mr. Kolawole. Thank you very much.
And to Engineer Felix too.
Okay, thank you, sir. Is there any other person that has his answer now, or I should just go ahead? So, from the answer, I've gotten answer for 1, 2, 3, 4. That's about 20% of the class, or 30 thereabout, which I believe for me is not so good. I want more participation from everybody. Basically, because this is a sizing class and you need to be involved in the sizing. This is very important for us all. So please, you need to be involved in every stage of this calculation. And I believe for those
even
that...
if you are wrong, just state your answer. Even if you are wrong, then you can
Yes.
correct it.
Exactly. Whatever
So
you get, just
know that. Yes, go on.
Yes, state it so that we help ourselves to understand the question. So, however, from what we have solved so far, we can see, Mr. Chigoze, I'm not sure if we are using the same Excel sheet because your answer is different, or maybe you are doing something differently. Let me use that word, because your answer is different from what every other person.
Sir, I'm using the same set you just dropped that has a total.
I have my answer now.
Somebody said he has his answer, and who is that? Go ahead and give us your answer.
That's Bella.
Mr.
I have
Bella,
12 strings, sir.
12 strings.
12
okay,
strings.
What's the total battery capacity?
48.
Sir?
Okay, the capacity 2234.03 ampere.
234. Okay. Ampere. So
234.03.
Okay. I get that now. Thank you very much, Mr. Bella. So far, from what I also worked on here, my total battery capacity is 2218. And this is the slide. I think let me just share my screen already so that we'll see what is happening here. This is what this is. Can you see the Excel sheet on the screen? Mr. Felix, please confirm that.
Yes, I can see it.
Okay, so basically what we are doing now is just to factor in our inverter efficiency, inverter conversion loss. If you take it to this, and also factor in our depth of discharge. It will take it to this, and now factor in our system voltage. It will take it to this. So this is what your capacity should be, 2218.22. And if you are using 200 Ah battery, if you are using 200 Ah 12 volt batteries, it will simply take us to 11.09, which in reality we will have 12 strings. So we should have 12 strings. 12 strings is correct. And for those of us that have 2218.22, you are correct. So Mr. Chigozie, kindly check that you are using the same Excel sheet as what I have on the screen now, and check that your refrigerator.
I've seen it.
You've seen it now. Okay, that's
not
good.
using the same Excel sheet. I'm using another Excel sheet I saw.
Okay, so what is important is for us to understand the whole concept very, very well. And we are almost at the end of today's class, and I believe that so for take-home assignment, that before your actual presentation, I'll be sending your presentation assignment. Okay, let's just leave it at presentation. I would say for practice, you should practice with making this system a 24 volt 100 ampere hour battery system, such that you will be able to just see what it feels like. So I would stop here today, and I would ask if Mr. Eric has any short comment, as you have less than 3 minutes to go. Mr. Eric.
I think it would be best if I kept quiet, since we are down to just 3 minutes, but thank you for the opportunity.
Okay, thank you very much, Mr. Eric. Yeah, thank you, sir. So Mr. Felix, I believe I can hand over the class to you at this point.
Not yet. What about every single person? Have they turned in the answers or not?
Okay,
so like Chigozie now, he said he used another Excel sheet. Which Excel sheet was that? Or is that?
Okay, so Mr. Chigozie, can you now work with this particular Excel sheet that we all worked with, and let us know that you have the same answer? So for everybody now, I would expect, for those that have not turned in their answer, if you have it now, please unmute your mic and give it to us. If you don't have it, I would expect it in the WhatsApp group. You have to turn in your answer today for this exercise. Let's do it. You have to turn in your answer in today for this exercise. I'll leave it up to 7 p.m. so you can turn in your answers. And if you are turning in your answers after now, it means you are showing workings now, because now we are no more in class. I was just expecting you just give me your direct answer. So for those that have called their answer and they are correct, they don't need to turn in the answer. So that goes for Mr. Femi, for Mayowa, and for Mr. Kolaoli. Mr. David, your answer was off at some point, though you have 12 strings. You need to recheck your calculation. Or is it Mr. Biola, the last person that gave his answer? So you send in your workings also. You can just take a snapshot of your exercise book page that you solved it, or your screen that you solved it, a screenshot, and send it to the WhatsApp group for us to see your answer and look at it together. So everybody needs to participate in this. This is sizing. This is the core of the SPVI. If you get it right from sizing, it's most likely you have gotten everything you need to know. So please, let us take this serious. We are all going to expect your answer for this, for everyone that has not mentioned or sent. So for those of you that have sent, if you also want to send your workings, so you can send that to the group too. So for those of us that have not sent, you have up until 7 p.m. Okay, let me just extend it 9 p.m. today, because I believe maybe some of us are at work and you still need to go home. And let me believe you're in Lagos, and with Lagos traffic and every day, you get home by 10 p.m. So by 10 p.m., I would expect that everybody has turned in their solutions. And Mr. Felix, since you have the list of everyone, you check who has not at 10 p.m. or tomorrow morning we'll know who has not turned in his answer. So I would also, since we are doing this, so go ahead and do for 12 volts 100 ampere hour 24 volt 100 ampere hour battery configuration for this same Excel sheet, and turn in your answer also. So now you are submitting what we have done in class, and you are also using 12 and 24 volt system voltage with availability, or according to Mr. Ari, you got a good price for the 100 ampere hour battery. So you have 100 ampere hour battery, 24 volt system voltage. So solve that with this same Excel sheet, including this last one that has refrigerator, AC, and electric kettle all on it, and send in your answers to me before 10 p.m. tonight. So, Mr. Felix, I hand over the class to you now. Thank you very much.
Very much, okay, Chigozie, go ahead.
Yeah, I didn't get Mr. Tunde's statement. It was somehow cracking.
Okay, what he said is, or if you want to hear from him, Engineer Tunde, you can explain to him.
Okay, Mr. Chigozie, can you hear me clearly now?
Yes, I can hear you now. Thank you.
So what I said is, for those of us that didn't get the correct answer for this exercise, go and do it again and send in your answers. You have up until 10 p.m. today to send in your answer. Then now I say you should go ahead and also do same as though you have a 24 volt system. Your system voltage is 24 volt and you have 100 ampere hour battery available in the market. So now you are doing another assignment that is for 24 volt 100 ampere hour, using the same data that we worked with. So that is what I said. I believe you now understand that. Mr. Kolawole, your answer.
Thank you,
see your answer. Do you want to say something, Mr. Kolawole?
Yes.
Yes, sir. I'm sorry to pick it up. Yes, I would just appreciate if you put it in the group, this additional requirement, so that everybody will not say, somebody will not say you didn't get what you said here. So if it is expressed in black and white and sent to us in the group, we can really appreciate it. Thank you, sir.
Okay, thank you very much, Mr. Kolawole. Mr. Felix, go ahead.
Yes, thank you very much, Tunde. It's very good that everybody partakes in the exercise, so that we know where our lapses are, what we don't understand, and areas we need to improve on. So this is very important. If your answer is wrong, it doesn't matter. Then we can trace back the steps that we missed. Thank you very much, Eric. Tunde, David Amoni, I can see your hand up. Quickly, go ahead.
Sorry, sir. I just wanted to ask Mr. Tunde if he can help us on the Excel that you just solved now. Indicate at what point, we just get into from 28748.1 as the total. What did you divide with to get, so just the breakdown so that we understand it at any time, a point in time.
Okay, so at first, after getting your daily energy requirement, so you go ahead and divide by the inverter efficiency of 90%. So it takes you to 31,942. Then after that, we go ahead again and divide by the depth of discharge, and at which we have been working with 30% also. So it gives you another, it brings you to 106,474. And finally, we'll now divide by the system voltage of 48 volts. And that will give you 218.22. And if you look at how many strings that will give you, that will amount to, at 200 ampere hour, that will be 12 strings. That is what happened. So solve this. Also play around. I believe if you have time, also try and work with 50% depth of discharge, 80% depth of discharge, just to play around with the analysis and see the implication on the number of batteries and the number of strings. Thank you very much. Mr. David, do you?
Thank you, sir. Thank you very much, sir.
Yeah.
Yeah, thank you very much, sir.
Thank you. So I know you post what Mr. Kola said. So it's a wrap. I'm sure you're going to get presentation questions to them, which we'll be having on Friday. So that's it from my end. So if anyone has any questions or clarifications, you can just put it on the WhatsApp group. Time is fast spent. Thank you, everyone. Thank you, Eric. Thank you. We're not having any class tomorrow and Thursday. So on Friday we have the